Okay, in this section, we're going to talk about objects moving through fluids and some of the interesting, fun phenomena that results. And sports provides one of the most direct ways that many of us, I think, in our everyday lives see some of the interesting effects of objects moving through fluids. As I said in class, how does a pitcher throw a curveball? What is it about the spin of a soccer ball that lets a striker, curve a free kick around a wall of defenders? When you're playing tennis, why do topspin shots seem to dive down faster than you expect after they cross over the net? And so in this kind of not very mathematical, but very qualitative section, we're going to use all of the concepts that we met in the previous part of this chapter to start explaining all of these phenomena. Okay, so I'm going to start out with section 7.4.1. 7.4.1, slow-moving things. Slow-moving stuff. And this is about basically laminar airflow around objects. So any object that's moving through a fluid is going to experience fluid dynamic forces. These are forces that are exerted on the object because it has relative motion through the fluid. Okay? So when that fluid is a gas, these are generically called aerodynamic forces, even if the gas isn't air. And when the object is a liquid, we usually call it hydrodynamic forces, even if it's not water. So we'll say in general, relative motion of an object through a fluid. And in this section, I'm really going to be thinking about moving through a gas. So I'll just say an object through the air. Relative motion of an object through an air introduces aerodynamic forces. Aerodynamic forces. And one of the most important of these forces is drag. Right. So drag is a force that kind of points downwind of an object that typically tries to slow it down. So if I have a ball and I throw it through the air is constantly bombarding the surface of the ball, slowing it down. There's a drag force. Okay. So drag, we'll say this acts downwind of an object. And then there are lift forces. And colloquially, we usually think about lift, like maybe of an airplane, as something that points up. But actually, we'll call lift forces things that act either up or down or left or right. Relative to flow. Right? So drag will be something that's slowing it down, acting against the object's velocity, if you will. And lift is an aerodynamic force that will point in any other direction. Okay. Great. So all of these types of forces turn out to start to get a lot more complicated as the relative speeds of the object and the fluid it's moving through get bigger and bigger. Right. So the more turbulent flow of air around an object is, the more complicated these drag and lift forces become, and the harder we have to think about what's actually going on. And so in this section, we're going to steadily think about increasing the Reynolds number. And remember, the Reynolds number, we could write as the density of the fluid times a characteristic length scale times a velocity, the relative velocity of the object and the fluid divided by the viscosity. So if I'm thinking about, say, a soccer ball moving through the air, the viscosity of air is not going to change, the density of air is not going to change, and the size of the soccer ball is not really going to change. So the change in Reynolds number will really just be a function of, is the soccer ball moving really slowly? Is it moving really quickly? And that will control whether we need to think about slow-moving, smooth, laminar flow or complex turbulent flow. So that's why the organization of this section of the chapter is going to be kind of from slow to fast. But what I really mean is increasing Reynolds number, starting out with small Reynolds numbers. Okay. So another thing that I'm going to point out is that in these problems, just like in any problem, we get to choose the frame of reference that we want to work in. Right? So it doesn't matter if I have a ball moving through still air or air flowing over a ball at the same relative motion, actually the patterns of flow will be the same. Okay, and so in this section and in the subsequent sections, I'm going to choose a frame of reference that's moving with the same velocity that the ball itself does. So in that frame of reference, for instance, the ball will look like it's staying still, and we'll be drawing the flow of air over that ball. It's just kind of a point of convenience. We can work in any reference frame that we want. Okay, so let's start out by considering, for instance, a soccer ball that's moving really slowly through the air. Okay, and I'll figure out what I mean by really slowly a little bit later. So if the ball is moving slowly enough, then the flow of air around it is going to be nice and smooth and laminar, right? And so what'll happen, actually let me give myself a little bit more space here. Let me draw the flow of air. Far away from the ball, air is just going to be flowing in these nice kind of streamlines that don't really feel the influence of the soccer ball whatsoever, right? I keep saying it, so I might as well write soccer ball. Okay, not going to feel the influence of the soccer ball whatsoever. On the other hand, air that's kind of headed right towards the soccer ball, what's that going to look like? It's going to start out moving towards the soccer ball. It's going to get deflected around it, and then it's going to come back behind it. And you should see the lecture notes where I do a more careful job of making sure everything is nice and symmetric, right? Because the way that it kind of goes down from here is the same as the way it rises up from here, right? So we've got these streams of air flowing nicely, smoothly around the soccer ball. I'm imagining the ball moving from right to left. So if I'm in the frame of reference of the soccer ball, air is flowing from left to right. Nice, smooth, even flow. Okay, and so what we see here is, in this nice, smooth, laminar flow, the relative motion is so little that, everything stays laminar. These streams of air kind of cleanly separate from each other in the front of the soccer ball, join up behind the soccer ball again as it travels, and the wake of air, which is this kind of trail of air behind the soccer ball, is also smooth and laminar. Everything's nice. Even though the flow here is so smooth, there are still these kind of dynamically generated variations in the pressure and the airspeed of the air as it flows around the soccer ball, right? So just like we saw in the case of the bent pipe, when the air is forced to bend, there's going to be changes in the pressure associated with that. So what does that look like? Above and below and to the left and right of the soccer ball, so if the ball is traveling this way, I mean all around the ball like this as it goes that way, there are these regions of lower pressure air, and just like we were thinking about this fictitious pressure potential energy that helps us keep track of how pressures and velocities of fluids relate to each other, this lower pressure air has lower pressure, higher speed. And there are these pockets of air in front of and behind the soccer ball that are just the opposite. So these pockets of air are going to have higher pressure, and lower speed. Right? So, as air starts moving towards the soccer ball, it sees this region of higher pressure. We know that fluids want to accelerate from regions of high pressure to regions of low pressure. So it starts bending around the soccer ball towards this low pressure region. And then it continues to kind of follow the soccer ball, a combination of it accelerating in response to changes in pressure. So here, as it goes from low pressure, it tries to bend away from this high pressure region, and that makes it kind of hug the soccer ball and join up behind it. And of course, the air also has its own momentum, and the combined effect of that is, again, the air approaches this high pressure region, it accelerates away from it towards a low pressure region, and then again accelerates away from the high pressure region and starts flowing smoothly out the back here. Okay. Great. So we have this kind of interesting pattern of laminar flow when the ball is moving sufficiently slowly. Again, air moving directly towards the ball gets bent away, so there's this high pressure region in front of the ball and an equivalent one behind the ball, and there are these lower pressure regions around in a ring around the soccer ball. Okay. In this case, we see that the airflow around the ball is extremely symmetrical, right? There are these low pressure regions that are totally symmetrical all around the ball as it travels this way, and there are these balanced regions of high pressure in front of and behind the ball. Okay? And that's really important. The fact that these high pressure regions are the same in front of and behind the ball, and the low pressure regions are the same all around the sides, mean that all of those pressure forces, and remember, pressure is like forces over an area, and so the air in contact with the soccer ball is exerting forces on the soccer ball. All of those pressure forces cancel each other out. And so the only aerodynamic force here, is a particular type of drag called viscous drag. This type of motion overall, I'd say, is pretty easy to think about. There's nothing kind of weird or unexpected happening, but it's also the case that only kind of the slowest motions of an object through a fluid have this nice laminar character. I'll calculate for a soccer ball what the Reynolds number is, what the velocity has to be to stay in this nice smooth regime. Okay. But in this case, the key message is when we have these smooth, symmetrical laminar flows, all of the pressure forces cancel each other out. You just have viscous drag of trying to move an object through a fluid. In this case, a gas, and the viscosity of air is really small, so this viscous drag is not very big. Okay. Things are going to get a little bit more interesting and complicated when we think about, let's say, medium speed motion, and onset of turbulent airflow. Okay, so if there's laminar airflow, the ball is just experiencing a viscous drag that's slowing it down, but there's no other aerodynamic forces. Now, when the Reynolds number starts to get a little bit higher, we know that the fluid flow becomes not laminar, but turbulent, and things start to get a little bit more interesting. So, what does this look like? Maybe let me cut and paste a little bit here to save myself some illustration. Maybe this isn't going to work that well. Sorry about that. So again, these red regions, just as before, are going to be regions of kind of higher pressure, lower pressure and higher speed. Higher speed flowing air, higher speed air. Now, what happens when we start crossing the threshold of, remember that kind of Reynolds number value of bigger than about 2300? Is that the airflow here starts to become not laminar, but turbulent. So we have laminar flow approaching the ball because it hasn't had a chance to influence, the air out in front of it yet. But the soccer ball starts leaving a turbulent wake behind it, right? And so in this turbulent wake, the airflow is no longer smooth and laminar and, easy to think about. It's this complex swirling set of vortices and backflows and all of this stuff. And you actually get this little reversing current of air near this part of the soccer ball that kind of feeds into the wake. Okay. So the idea here is that once the soccer ball starts moving fast enough, the viscous forces in the air, the viscosity of the air, is no longer strong enough to completely bend the laminar flows like here all the way back around the soccer ball, right? And so because those viscous forces aren't strong enough, there's going to be a boundary layer of air that's seeing the high pressure region behind the soccer ball. That high pressure region at first gets so big that it kind of completely stops the air that's coming towards it, and then eventually reverses its flow and leads to this kind of turbulent wake. Right? So this really radically is disrupting the flow of air around the ball. We have this huge wake of turbulence behind. And in kind of most of this turbulent wake, actually on average, the wake is at, I guess this is where my picture is going to be, so I'll draw it down here. The turbulent wake is basically at atmospheric pressure overall. Okay. But we start to see, and because of that, we start to see that the patterns of pressure are no longer totally symmetric, right? We still have this symmetric region of low pressure, high speed air around the sides, top, and bottom of the ball. But we no longer have a high pressure region behind the ball, which cancels out the high pressure region in front of the ball. Okay. This is called pressure drag, right? So what's going on, again, is we have this high pressure region of air, and that high pressure region of air is exerting pressure forces on the surface of the soccer ball that are not balanced by a corresponding region of high pressure behind the ball. Right? So in addition to viscous drag, so let's say here, in addition to viscous drag, there is pressure drag. There's pressure drag. If you want, you can also think about what's going on by thinking about ideas of momentum conservation from earlier in the class. Right? So the idea here is that this turbulent wake has air molecules that have had their velocities changed by a lot. Maybe the overall speed of the air molecules isn't so different, but we've radically changed the directions of a lot of velocities of all these air molecules. So the air molecules in this turbulent wake have taken a lot of momentum. And where did that momentum come from? It came from the momentum in the soccer ball traveling forward, right? So if you like, some of the effects of pressure drag you can think of as, the soccer ball losing momentum to the turbulent wake behind it. And just so that you have a sense of, not numbers, but just like qualitatively, how big a deal is pressure drag? Pressure drag scales like, so is proportional to the cross-sectional area of the wake, of the turbulent wake, multiplied by the velocity, the relative velocity of the ball through the air squared. Right? So viscous drag just depends on the velocity itself, velocity to the first power. Pressure drag depends on speed squared. Okay. Pressure drag just happens, pressure drag depends on speed squared. And that means if you have a fast moving object, the faster it moves, really the much faster the pressure drag increases. Now, when I say this is kind of medium speed motion, the regime that we're talking about here, regime of medium speed, is basically Reynolds numbers, which are bigger than this threshold. So it's not just laminar flow anymore, so it has to be bigger than this 2300 number, but it's less than, say, about 100,000. Okay. So when the Reynolds number is kind of in this regime, that's when you have this kind of medium speed behavior where you have smooth laminar flow. The boundary layer of air starts out flowing smoothly around the soccer ball, it gets disrupted, and then you have this turbulent wake behind you. So, let's be concrete. So, concretely, for a soccer ball, okay, so a regulation size soccer ball has a radius that's about 11 centimeters. It has a radius that has about 11 centimeters. And then if we use our formula for the Reynolds number, which is density of the fluid, in this case this is going to be the density of air, times this characteristic size of the soccer ball, times some velocity divided by the viscosity of air. If we plug in numbers for air, for the viscosity and the density, what we find is that a soccer ball moving at, I did this calculation over here, so a soccer ball moving at about 1 foot per second, about a third of a meter per second, has a Reynolds number of about 2,000. Okay, and a soccer ball moving at 33 miles per hour, which is like 15 meters per second. That has a Reynolds number of about 100,000. So one of the things that I want to emphasize is that actually, in the context of typical sports, something moving, a soccer ball moving at a foot per second, that's like really quite slowly. Like you have to work to get a soccer ball to move that slowly after you kick it. You have to not try, I suppose. So actually, the region of laminar flow, slow speed, for like sports, this almost never is what you're most worried about. This smooth laminar flow almost always gets disrupted because the Reynolds numbers are just too high. And actually, this intermediate region of speed, where you have laminar flow ahead of the ball and in a boundary layer around part of the ball, and then you're leaving this turbulent wake behind you, that happens a lot of the time. But even in soccer, it's not hard at all to kick a ball faster than 15 meters per second. In fact, professional athletes can kick a ball quite a lot faster than 15 meters per second. So that kind of maybe helps situate you that this kind of medium speed region is definitely more important when we start playing sports, but it's easy to go even faster than is relevant here. Okay, so great. So at low Reynolds number, the whole flow of air around, say, a soccer ball is laminar, smooth. And even the wake behind the soccer ball is just a small wake of very smoothly flowing air, right? In that case, the drag force was just viscous. At these intermediate Reynolds numbers, the boundary layer around most of the ball is still laminar, but the boundary layer can't make it all the way around the ball, and you get this large turbulent wake, and that creates a large pressure drag that slows the ball down a lot. Okay. So what happens when we go even faster objects? So Reynolds numbers that are like bigger than 100,000. What happens is that the boundary layer of air really close to the ball itself stops being laminar. So if I look at my picture here, and if I again just kind of grab a chunk of it to copy over, At this point, you might wonder why I'm even bothering with some of this stuff. Great. I still have smoothly flowing air far away from the soccer ball, but here, even this boundary layer here is already very turbulent. And actually, the result of that is that the wake behind the soccer ball is much smaller. It's much more turbulent. See, if you have an intermediate speed soccer ball, say, the boundary layer can kind of go from laminar to turbulent, like over here, for instance, and that can leave behind a very wide wake of turbulence behind it. But if the boundary layer everywhere around the soccer ball is already turbulent, actually the result is that you just have a very focused wake of turbulence behind the soccer ball, and you don't disturb as big a region of air. And so actually the pressure drag at these even higher Reynolds numbers gets a little bit smaller, because the pressure drag depends on the cross-sectional area of the turbulent wake, not the cross-sectional area of the object itself. And it turns out that effect is not particularly small. So just to kind of give you some context, I looked up numbers for a regulation baseball. So for a baseball, Reynolds number of about 100,000 happens when the ball happens for like a magnitude of the velocity of the baseball close to about 100 miles per hour. Close to about 100 miles an hour, okay? So that's that means most pitches are in this intermediate speed regime, but most batted baseballs, so after the ball leaves the bat, it's traveling faster than this typically, in professional sports anyway. So in baseball, you have this intermediate regime of Reynolds number for the pitch, and this high regime of Reynolds number for the batted baseball, okay? So the large kind of pressure drags that are influencing a pitch, if I have like a pitcher with a face, throwing a baseball, let's say at 90 miles an hour, by the time it gets to this batter holding a stick, whatever, the distance between a pitcher and a batter in baseball is only like 60 feet, I think. But the large pressure drags here will slow that baseball down closer to like 80 miles an hour by the time it actually gets to the batter. So there's a really substantial drop in the velocity of a pitched baseball in a pretty short distance. You know, the length of time it takes a ball traveling at 90 miles an hour to go 60 feet is not very long. But the pressure drag here can really be quite enormous, right? So the fact that after the batter hits the baseball, it's traveling, you know, beyond this kind of intermediate threshold Reynolds number is actually why it's even possible to hit a home run in the first place. If this ball was experiencing the same magnitude of pressure drag that the pitched ball was experiencing, it would never make it out of the outfield. And again, the reason is that this pitched baseball is leaving behind a much bigger turbulent wake than this more focused turbulent wake after the baseball is struck. Okay. This same effect, the fact that when the boundary layer of air around a ball itself becomes turbulent, it experiences less pressure drag, is why golf balls have little dimples on them. You know, one way to get a ball to experience less pressure drag is to hit it fast enough so that just, you know, based on the Reynolds number of how fast that thing is moving through the air, the boundary layer of air around it is already turbulent. And then it leaves this nice focused wake of turbulence behind it. Okay, as it flies through the air. That's one way to get a ball to reduce the total amount of pressure drag on it. The other way is to add little bumps and grooves and ridges to the surface of a ball so that when the air flows over it, it's like there's another bump in the way and the air starts becoming turbulent even at slightly slower velocities. So these little bumps actually increase the viscous drag on the golf ball because they increase the total surface area over which air and the golf ball are in contact. But that increase in viscous drag is more than compensated by the decrease in pressure drag for golf balls, you know, traveling after they've been driven. Okay, so one of the last things that I want to cover in this section, and this is already a little bit of a longer video lecture than I would have liked, but this last bit isn't too bad, is to think about curveballs, right? So far we've looked at situations where, you know, in smooth laminar flow, we have totally symmetric distributions of pressure around a moving object through fluid, so there's no pressure forces. At medium and higher speeds, there start to be unbalanced forces due to pressure, because there's equal pressure at the top and bottom and sides, but there's an unbalanced high pressure region in front of the ball that's not balanced by a high pressure region behind the ball. That leads to this pressure drag. Well, how can we arrange things so that now there's asymmetries not just in front and in back, but also around the sides and the top and bottom? Okay. So that'll be the subject of this little section. So I think we have an intuition for what trick we're going to play to get unbalanced pressures at the tops, bottoms, and sides of a ball, because we've probably seen, you know, a pitcher throw a curveball or a striker curve a soccer ball by giving it spin. But how does that work? And, you know, maybe you could ask yourself and pause and think about this. If you imagine a spinning ball moving through the air in your head, which way does it curve depending on which way it's spinning, right? So we can think about that for a quick second. Curveballs make use of lift, right? Make use of some of these lift forces. The idea here is that an object is going to be deflecting air asymmetrically or creating an asymmetric field of pressures around it in such a way so that forces are generated in a direction which is different from just against the motion of the object itself, right? And if you think about it, I mean, I think it's pretty cool. It's not immediately obvious how a spinning ball convinces the air to push sideways on a ball, for instance, right? So it turns out there are two primary mechanisms for a curveball. And once again, these two mechanisms, one of them operates when you have either laminar or turbulent flow, and the other operates only when you have turbulent flow. So we'll start with the one that it doesn't matter what kind of flow it is first, because it's kind of more general. So first is the so-called Magnus force. Okay. So the idea behind the Magnus force is the following. Suppose I have a soccer ball and it's kind of spinning in this direction, right? So now if I look at the streams of air that kind of go around this soccer ball, it's kind of, again, smooth and laminar, say, out here, and let me focus on the laminar case of the Magnus force for the time being, what happens? So I have this layer of air approaching the spinning ball. It bends around it, and the spinning of the ball kind of helps drag this layer of air around so that it actually ends up going kind of off in this direction. And I'm really exaggerating maybe how much the air gets deflected just for effect. Kind of like so. Right? And far away, there's still laminar flow like this, so in between, there's probably something that's kind of like so. So on and so forth. Okay. So this spinning object is basically helping to move some of the boundary layer of air that's right next to the soccer ball along with it. And that gives us this asymmetric pattern of flowing air. And if you think about the paths that this flowing air is taking as it moves around the ball, the long way, as I go the long way around, this way, the air has to really bend around more of the ball. And that means there's a much greater change in the direction as it turns towards, as it keeps having to turn towards the ball to kind of follow the curve of the ball around. In contrast, if I go the short way around, actually most of the time, this path is bending away from the ball. It's bending away from the ball here, and then it's bending away from the ball again here. There's not like a large chunk where it's bending towards the ball. Okay. So what did we learn earlier when we were thinking about these kind of, which way is the ball bending, et cetera, et cetera? Let me match the colors that I used up above. I guess I used green for high pressure. So if there are regions where the air is bending consistently away from the ball, I must have regions of high pressure and lower speed. And there has to be, in regions where I'm consistently bending towards the ball, right, this whole arc, it's like I'm accelerating towards the ball, I must have a region of low pressure, high speed air. All caused by the fact that the rotating ball is like dragging some of the layer of boundary air along with it, right? So what we see here is that we have this unbalanced set of both high pressure regions over here and low pressure regions on this side of the ball. And the net result of all of this, is a net force in this direction. And that's called the Magnus force. Okay, so as the ball, moves in this direction and spins this way, it's going to start to curve in the direction that it's spinning. Okay, Now, there's also this. It turns out, Magnus force operates regardless of whether we have this nice always laminar flow or if there's also a turbulent wake. And so the Magnus force always exists when you have a spinning object moving through a fluid. What happens if you don't have purely laminar flow and instead the ball is leaving a turbulent wake behind it? Well, it turns out the spinning of the ball deflects the wake. So if the ball wasn't spinning, the wake would be, going this way behind it. But in the presence of spin, the wake itself gets deflected too. And that could be a focused, narrow turbulent wake if the Reynolds number is really high, or it could be like a big turbulent wake if the Reynolds number is in this intermediate regime. But regardless, the wake gets deflected kind of to point in a direction that's kind of like that, as opposed to a wake that's pointing in a direction like this. Because this turbulent wake has been deflected away, we can think about that as, all of the momentum in that turbulent wake of air going every which way, was on average deflected from what the momentum should have been. So this wake deflection force actually also points in the direction of making the ball curve in the direction that it's spinning along, if you like. So both of these aerodynamic forces, both the Magnus force and the wake deflection force, tend to push the ball in the same way, making it curve in the direction of the spin, right? So if I was looking, top down on a ball and it was spinning clockwise, then I would see it kind of curve to the right. If it was spinning counterclockwise, I would see it curve to the left. If it had topspin on it, that means the lift force, the Magnus force, and the wake deflection force would point downward. So it would dive down due to these aerodynamic forces faster than it would fall just due to gravity. And similarly, if I give it backspin, there's going to be an aerodynamic force which points up, right? That's like what we usually think of as lift. And so the ball would fall more slowly than it would just due to gravity, right? So it would seem to like hang in the air a little bit longer than you expect. Okay. In case you're curious, knuckleballs, FYI, knuckleballs are actually characterized by a complete lack of spin. In baseball, the pitcher is trying as hard as possible to throw the ball very fast without giving it any spin whatsoever. And when they're able to do that, highlights the fact that baseballs are actually not perfect spheres, but they have these little seams of stitching that go around them, right? And those stitches are a little bit raised above the surface of the rest of the baseball. And when air flows over those seams at high speed, they can trigger local transitions to little pockets of turbulent flow for small like parcels of air around them. So by not spinning and just having these like localized pops of turbulence, a knuckleball will move really erratically as these little pops of turbulence kind of deflect the ball a little bit in one direction or another. Okay, that's a quick aside. A fun fact about the Magnus force. I think it's a fun fact anyway. Fun fact. I said the Magnus force. The Magnus force is present for any rotating object moving through a fluid. And people have used that to design what I consider to be hilarious sailboats. Usually we think of a sailboat as a boat that has like a mast and like a sail, and the wind fills up the sail, and there's a force on it, and then the hull of the boat helps convert the force of the wind acting on the sail to forward motion of the boat. What some people have been doing for a long time now is that you can design a different type of sailboat. I hesitate to even call it a sailboat, but I don't know what else to call it, by replacing the mast and the sail with just a giant rotating cylinder. So you've got a boat, you've got a motor. Rather than like have a little engine that sticks up off the back with a propeller that like moves water behind it, you attach that motor to a giant cylinder sitting on top of your boat that's spinning around. So now, if there's any wind, wind will come and blow across this rotating cylinder. That will create a Magnus force that's pointing, just like in this case, kind of slightly diagonally, but in the direction of the spin. And then you can design the hull of a boat so that it converts that Magnus force into forward momentum, forward motion. And bizarrely enough, these things actually work. And in some cases, they can even be energy efficient ways of having a motorized vehicle, which depends on the wind for propulsion, but not by sails, just by these rotating cylinders. And in the lecture notes, I have an example, an image of like a massive version of one of these ships.